All right, people, welcome back. So today we're going to use logarithmic functions for something very good. Namely, we're going to use them to solve some equations that have exponential functions in them. So let's start here with this first fact, that if we have b to the x equals to b to the y, then x must equal to y. In other words, I think we already know this, that exponential functions are 1 to 1. That's all this really says. So in particular, what is the inverse of an exponential function? But if we have base b, then the inverse is log base b of x. So we have an expression like this, b to the x equals to b to the y. What we can do is just take log base b of both sides, and then we get x equals to y. So we'll do that here in the following few examples. So in the first one, we have 2 to the 3x minus 1 equals to 32. But we know that 32 is 2 to the 5th. This helps us. So now we can write this equation with the same base on both sides. So we have 2 to the 3x minus 1 equals 2 to the 5th. So now we may take log base 2 of both sides and cancel out the exponentiation. And we just have now that the exponents must be equal to each other. So that 3x minus 1 equals to 5. And thus 3x equals to 6. And so x equals to 2. All right, in the next one, we're going to have a common base of 4. We have here 16 to the 1 minus 2t equals 1/4 to the t. Now notice that 16 is 4 squared. And 1/4 is 4 to the minus 1. So we can write this equation as 4 squared to the 1 minus 2t equals to 4 to the minus 1 to the t. So now using the property of exponents, which says that if we have 4 squared all raised to the 1 minus 2t, that becomes 4 to the 2 minus 4t. You multiply through, so 2 times 1 minus 2 times 2t. And likewise, on the other side, we have 4 to the minus 1 raised to the t. That becomes 4 to the minus t. And so now we have the same base on both sides, so we could take log base 4 of both sides, and we'd be left with just having the two exponents equal to each other. So we have 2 minus 4t equals to minus t. But then we can add 4t to both sides, so we get 2 equals to 3t, and thus t equals to 2/3. Okay, in the next example, it doesn't look like we're going to have the same base on both sides. I don't know anything that sort of makes a sort of commonality between 5 and 12. We have 5 to the x equals to 12. So since there is no apparent common base, let's just take one logarithm of both sides, and I'll just pick the natural log, because since there's nothing in common between the two, we might as well just pick any old base that we like. I like natural log base e. So natural log of 5 to the x should then equal to natural log of 12. And so then we can use the property of logarithms, which says that if we have an exponent up here, it gets to yank outside and come downstairs. So the left side becomes x times the natural log of 5 equals to the natural log of 12. And now, natural log of 5 and natural log of 12, they are just numbers. They might not be very pretty numbers, but they are just numbers. So here we have x times some number equals some other number. The way we solve for x and isolate it is just divide both sides by the scalar that's multiplying x. So we conclude that x equals to natural log of 12 divided by natural log of 5. Otherwise, we could say that this is something about 1.544. That's what I took to my Texas Instrument to find out. Okay. So then, so we've already, I think, recalled this, that log base b is the inverse function of b to the x. So we'll have that log base b of b to the x equals to x. We've already used this a few times today already. So we'll use it a couple more times in the next example. So we have here that we will solve for x. We have 5 times e to the 2x minus 1, all minus 9 equals to 30. So the key here is to isolate the exponential function. And then once we isolate the exponential function, then we'll take a logarithm of both sides. So here we go. So I'll write 5 times e to the 2x minus 1 equals to 39, just from adding 9 to both sides. And now if I want to isolate the exponential function, I'll divide both sides by 5. So I have e to the 2x minus 1 equals to 39 divided by 5. And now with the exponential function isolated, I can take the logarithm of both sides to cancel out this exponential function. So I will choose log base e since I have base e over here. And so I also just prefer natural log whenever I can use it. So here we go. So here we go. We have natural log of e to the 2x minus 1 equals natural log of 39 over 5. But natural log is the inverse function of e to the stuff. So these two operations cancel, and we're left with just 2x minus 1 equals to natural log of 39 over 5. So now we can add 1 to both sides, and we get 2x equals natural log of 39 over 5 plus 1. So divide both sides by 2, and we solve for x then that x is natural log of 39 over 5 plus 1, all divided by 2. And if you don't like this sort of stacking of the fractions here, you might recognize that this logarithm of a fraction can be written as a difference of the logarithms. So another way we could write this answer is natural log of 39 minus natural log of 5 plus 1, all divided by 2. Same answer. So either one is fine. OK, let's see one more of these. So we'll have 10 to the 8x minus 3 plus 4,500 equals to 24,000. So again, the first thing I'd like to do is isolate the exponential function. So that is, in this case, 10 to the 8x minus 3. So I will subtract 4,500 from both sides, and I'll be left with 10 to the 8x minus 3 equals to 19,500. So now I will take log base 10 of both sides, because I see here log base 10 on this side. So log base 10 of 10 to the 8x minus 3 is just 8x minus 3. And then log base 10 of 19,500 is on the other side. OK, so now I will add 3 to both sides. And we have 8x equals log of 19,500, all plus 3. And then divide both sides by 8. And so we get our final answer to be x equals to log base 10 of 19,500 plus 3 over 8. All right. OK, and the next example is a little bit different, so I think we'll make a new video for that one. We'll see you then.